Okay. Last couple of announcements. We're in the first week after midterm. And on the academic calendar, they have listed there that midterm progress reports are due. Okay? Now, what does that mean? That means if they open that up for us to do them, we're required to put any students who have D's or F's at midterm. So far, I haven't looked lately, but I don't know if last time I looked, they didn't have them open. They usually are a little late getting them open. They could be open now, I just haven't looked lately. But if they do, then I have to put anyone who has a D or an F at midterm. Right now, only uno of these 10 students in my good Math 113 pre-calculus trade class has turned in a paper. And only 7 of the 10, meaning 3 students, have not turned in anything. Okay? So if they open this, and I'm preaching to the choir here, I think, if they open this, then I'm required to give those 3 students either D's or F's. Otherwise, no, I'll have to say they're failing at midterm because I don't have any scores from them. Now, you've had those first tests for more than a month, okay? Because the first one was turned in back on the 9th of, somewhere around the 9th of February. So it's now the 9th of March. So yeah, it's been right at a month. Well, no, since the first one was turned in. You had it a week or so before that. So please, folks, get moving on those tests. Because I'm pretty sure that I have, let me just make sure of this because yes, I do have test 2 copied and ready to give you. I will be giving you this today. Y'all have turned in test 1. 3 people have not. So please, folks, get them in. Now, one other thing, I think I announced this before too, but just to make sure that you know, my office hours changed once second mini term began, and on Tuesday and Thursday, I was office hours 10:45 to 12:30. Now they're 10:45 to 1:15. So a little bit longer office hours on Tuesday and Thursday. Monday, Wednesday and Friday stay the same, but Tuesday and Thursday, I'm in the office 45 minutes longer on each day, which means I'm here on campus 45 minutes later each day. But that's beside the point. Okay. Any questions on anything we've done so far? All right. Now, let me get this slideshow set up from current slide. And this was the end of example 2. And where we're beginning now is called trigonometry and bearings. Okay? Tyler told me he worked at a auto place, so y'all deal with bearings a lot, right? That's the different kind of bearing. Okay, never mind. Okay, so what are we talking about here? In surveying, in navigation, flying aircraft, moving ships around, whatever, directions are often given in terms of bearings. Okay? If you're in the military, targeting is done in terms of bearings. You won't get to firing any rockets or any self-propelled grenades or anything yet. So, we're dealing with bearings. A bearing measures the acute angle that a path or a line of sight makes with a fixed north-south line. Okay? So, let's say, just make a wild guess here, that's approximately due north. May not be exactly. Let's just say that's due north. So I'm looking at an acute angle from there. If I go east of north, that would be this way. So I'd be so many degrees east of north. If I went this way with an acute angle, that's that's so many degrees west of north. Say again? Okay? Go back to the front. Okay. Now, this is south, and remember that north-south line, then so many degrees west of south or so many degrees east of south. Those would be our bearings, and we can keep them all to be acute angles, unless we're going due east or due west, and then it's exactly 90 degrees. Okay, a bearing measures acute angle. Okay. For instance, the bearing of south 35 degrees east. Face south, go east 35 degrees from that. That would be this right here. Face due south and go east 35 degrees from there. Okay? This is north 80 degrees west. Look north, go almost due west. 80 degrees due west would be 10 degrees short of due west. So that would be north 80 degrees west. This is north 45 degrees east. Look north, go 45 degrees, halfway bisect between north and due east. And that would be north 45 east. Now, the main thing to note here is, I guess, 2 or 3 main things. Before, we always took our positive horizontal axis as where we measured our angles from. With bearings, we don't. We either are looking north or looking south. So usually we represent those vertically up or vertically down. Number 2, before we did positive angles rotated to the left, counterclockwise. Okay, now positive angle is any acute angle left or right of north or south. Okay, so you don't follow the same conventions either in where our zero is or where our positive and negative. In fact, with bearings, we don't use negative numbers. We always use positive numbers. We go east or west rather than saying positive or negative. Okay, does that make sense? Okay. So here's example 5. A ship leaves port at noon. Port is over here at A. Okay, let me get my pen darkened. Okay, darkened. Okay, there we go. Hope it's there. Yeah. Okay, so port is over here at A. Ship leaves port at noon and heads due west. We hope this is on the west coast, otherwise he's just piled into the due west at 20 knots. Does anyone know what a knot is? Okay. A knot is a nautical mile per hour. Well, is that any different from a mile per hour? Huh? Yes. How much? What is a mile in terms of yards?
It's like 5,000 feet.
That's feet. 5,280 feet, which would be 1,760 yards. I know you played sports. Did you ever run track?
I ran cross country.
Cross country. Oh, okay. In the old way, when we used to use the U.S. English type things, one round around the football field was a 440 yards. Okay? The 440 dash or sprint or whatever you call it. 2 times around was 880. That's a half mile. So double that, 1760. Okay. They don't use it anymore. So back when I was in school, that's what we used. Okay. So that's what a mile is, 1,760 yards. A nautical mile is 2,000 yards, just a little bit longer. So 20 knots would be a little bit faster than 20 miles per hour, maybe 21, 23, 20 something. Okay. Amber's here. Okay.
So you said 20 knots would be a little bit more than 20 miles an hour?
Yes, exactly. Because a nautical mile is a little bit longer than a statute mile is what they call it. Yeah. Or 20 nautical miles per hour. Nautical miles, 2,000 yards rather than 1,760 yards. Now at 2 p.m., okay, so 2 hours later, that was noon, he left port. So he traveled 2 hours due west. How far did he travel? 40 nautical miles, exactly. And at 2 o'clock, he change course to north 54 degrees west. So act like you were heading north of 54 degrees, which is not a very sharp turn, because how much? Well, okay. North 54 west. That's how you describe it. And he keeps the same speed. Find the ship's bearing and distance from the port of departure, at 3 p.m. So just 1 hour later, he's gone 20 nautical miles in this direction. So what we want to get is his bearing from port, and they've shown this, that the beach over here is due north, and the bearing would be the angle here, due northwest, north so many degrees west, and then the distance would be the length of sea there. Okay? So, how in the world are we going to figure that? Okay, we want to know what C is one thing. That's the second part of the question, the distance from the port of departure. The other thing is the angle at point A between the dotted line and the horizontal. No, between the vertical line and the dotted line. Okay? And you sort of zoomed in on the distance, which I think that's the best way to go. Let's do the distance first. How are we going to determine how far, how long C is? Up until point B, right? Yeah. So you know it's more than 40 nautical miles this way, and then it's going to be something more here and something more there. Okay? So maybe we need to focus on this little triangle here. That's going to give us our two somethings we don't know. Okay, now we know this angle is 54 degrees. Does that tell us anything about any other angle? That's not in this triangle directly anyway. Okay, and we know this one's 90, so we know the sum of those two is
45.
No, it's 90. The sum is 90, right? Oh, so 3 added together, 180. Subtract 90. Okay, but we also know that the sum of these two angles is 90, right? Because that's also a 90 degree. So we do know this 54 is the same as that. Because this angle plus this is 90, this angle plus this is 90, this is the same angle, so this must be 54 degrees up here. Do you buy that? 54 degrees. Okay, Kamari's here. I think that's Kamari. I've seen him somewhere before. Haven't I? Okay. So we got half the class here. That's good. All right. And by the way, I was telling the others before you came in, we just passed midterm. It was, I think, midnight Monday. So sometimes they ask for midterm progress reports, that first week after midterm. As far as I know, they haven't asked for them yet, but I'm going to check my stuff either later today or Monday or tomorrow. I hope to have time to do that and see. If they do, then I have to report anyone who has a D or an F at midterm. And I was telling the class earlier, there's still 3 people out of the 10 who haven't turned in anything yet. No paper and no first test. So if you know any of those, please let them know. I need something in sooner rather than later. Either your paper or your test or both would be even better. Okay. So here we have, that's 54 degrees. How does that help us in any way whatsoever? Okay, this is going to, that's 36, isn't it? We also know this is 36 degrees. That's interesting and fine. But how does that help us find C? That's what I understood you were interested in doing. How the distance from the point of departure. Okay. What does C look a lot like? Hypotenuse. It surely does, doesn't it? Hypotenuse of what? Okay. Opposite this angle C. So if we knew this B here, which is opposite that, and knew this D here, we already know this length here. We could know the two sides of the right triangle, and we could calculate the hypotenuse of the right triangle. Okay? So, does anything here enable us to do that? We know the 40, we don't know this little d or that little d. This, by the way, is a right triangle. A little okay, which trig function you want to use, and which angle you want to use. You got two to choose from, 54 or 36, I don't care which. Say again? Do 36, and what are we going to do with that 36? What are you looking for? B or D or something else? D? So what trig function relates this angle 36, that length B, and what we know, the only thing we know in this triangle besides the angles is that length there. Sine will do it. And how does that go? Tell me the equation. Sine of 36 degrees is equal to B over 20. Got it. So we can get B right there by multiplying both sides by 20. And the 20s go out there, and you have B is equal to 20, that's nautical miles, times the sine of 36 degrees. Someone punch that in and see what you get. $11.8 nautical miles. Okay, so B over here is 11.8 nautical miles. Let's see. Okay, I'll write it down. 11.8 nautical miles. I was just wanting to make sure they got the same thing we did. It looks reasonable. Okay, how about for D down here? We could, so let's do it. D is equal to, or you could do it some other way if you wanted to. D squared, would you rather do that? Whatever. What would D be? The square root of what? Earth to class, come in please. Okay. Square root of what? Would that be 400, 20 squared, minus 11.8 squared? I don't have a, I can do one in my head, I can't do the other one very easily, so. Is that right, not right? This squared minus this squared is equal to, I mean, this squared minus that squared is equal to that squared. Or the square root of this is equal to that squared. This is equal to the square root of that. does that give you? What's that?
So why did you do that?
I thought you said use Pythagorean theorem. How did you do it?
C-squared.
What's that?
He did it, but it was basically like stalled.
So I got 539.24, and then you got to get rid of it.
And what?
I got 539.24, and you're in.
I think you added rather than subtracted. Is it Pythagorean theorem that b squared plus d squared is equal to 20 squared? Yeah. Okay. That's why I did it this way. Okay.
They use the cosine.
Okay, you can certainly do that. I asked you, you said use it, so I used it. Okay. You can also use cosine. Either way you want to, it's fine. Okay. How would cosine work? How would cosine work? It would be just like we did for B, only with D, it would be 20 times the cosine of 36 degrees. Let's do it both ways and see what we get. You decide which one you think is easier, harder, simpler, or obvious, or whatever.
I got rid of 260.
You got what?
260.76.
Before you took the square root?
Yeah.
Take the square root then.
16 point. Since we rounded to one digit off.
16.1
1.
nautical miles. Okay? Now, does that even look like it makes sense? Certainly the hypotenuse's got to be the longest. It is. But D looks like it's got to be longer than B because the angle 54 is larger than 36. It is. So that's in between those two. At least it gives me a nice warm and fuzzy that it feels about right. How about the other way? Did you do it the other way? You wanted to use cosine. 20 times cosine of 36. What did you get that way? You don't have to. You can do it only one, but you can do it either way you want to. You could have also done D is equal to 20 times the sine of 54. That would work too. Okay? But what did that give you? 20 times cosine of 36. Sure you're in degree mode, by the way.
Same thing.
16.1. Yeah, trick is nice that way, isn't it? You can do it several ways and get the same answer. So what do we do with that?
Yeah, 16.1, 40.
Okay, and that gives you 56.1. And what do we do with that?
Now we have two sides to each other. We can still do that again.
All right, and this time we do add, okay? So 56.1 squared plus 11.8 squared, take the square root of that, and you should get C.
$56.8.
56.8. 56.8 nautical miles. All right, let's see. Does that make sense? Well, it's got to be the longest of the three sides. Certainly longer than 11.8, and it's just barely longer than 56.1, but that looks about right. I mean, they're almost the same length. If you rotate it up, yeah, you'd just be a little short there. Or if you rotated this one down, you'd be a little beyond that. So I'm okay with that. That feels comfortable. Let's see what the book got.
Yeah.
57.4.
I put in the 8.
You what?
Put in the 8.
Oh,
I got
okay. All right, that feels a little better. Okay, 57.3. Okay. My eraser isn't coming up. There we go. They got 57.4. That's close enough for government work. Okay. Okay, nautical miles. See, we really don't have more than 2 significant digits anyway, so either one of those rounds to 57, so I'm okay with that. All right, that gives us our distance C. That was the second part of the problem. The first part, we still haven't gotten the bearing at D from point A. I can give you the directions. Can you? The bearing is measured from either due north or due south. Which do you think is going to be the acute angle? Due north. It's going to be this angle right here. That's the angle we're looking at. We're going to be north, that angle west. Because north, from north, moving toward west, that acute angle. We just got to come out. Let's call it A, okay? Because that's what they have in the book. Nah, that's not quite A, but close to it. I'm sorry. Probably should go down to here, okay? Well, no. How are we going to get that? Again, very similar to what we just did before, because this line is parallel to that line. They're both going due north, right? And this bisects, or is a transect, cuts across those two. Then this angle here must be the same as this angle here. Not the 54, but the one going between the dotted lines. And probably the 54 should not have gone to that one either. So it's this angle, okay? So this angle here and this angle here, which is greater than 54, they must be the same. All right? So if we're dealing with that, this is the angle, same as that one, that we're looking for. We know this side, and that side. You have your choice of ways to compute that angle. What would you choose to use? And that is the right angle still, right?
What are you trying to find?
Second?
What are you trying to find?
Trying to find this angle here because that's the same as this angle here. This angle here is what we're looking for, the bearing. From due north to here. What is the bearing of that boat from the point?
Add 34, 36.
Second?
Add 54, 36.
No, that's not 54 plus 36. It's 90. That's not a 90-degree angle. That would be here. This is less than 90. That's less than 90. 90 would be all the way to here. So it can't be adding those two. All we know it's greater than 54, because 54 was the angle from here. Is what? Okay, that is a distance. Oh, I didn't change that. Let me change that. Okay. This is 57.3. Okay. We're looking for this angle. That's the bearing north to west of this boat here from our, what is that? The ship's bearing from the point of departure at 3 p.m. That's where the ship is at 3 p.m. Its bearing is going to be that. From geometry, we know that angle is the same as this angle. Okay? So we're looking for this angle. This angle that we're looking for relates to two of the three. You get to choose. This side, that side, or that side. How does it relate to any two of those three? Come on. It's a right triangle. You know this side. You know. Oh, I erased the wrong one, didn't I? Yuck. Y'all let me get away with this. This was our 56.1 down here. That's this whole length down here, from here to there. The 57.3 was up there. Okay. Sorry. Say again? Okay. We've got the nautical mile answer. C, we got that. Now we're looking for a bearing. So let's not add or subtract nautical miles to get a bearing. Okay. Find what?
D.
D here? We already found that. 16.1.
Oh, that's what you just asked.
We're trying to find this angle here. Now, there's not a lot to give it to us until we look and see it's the same as this angle here. This angle here, in our triangle we've got here that we know all three sides. How do we get that angle? Hint, we only need two of the three. You get to choose which two you want to use. Which two you want to use. The two legs, the opposite leg, the adjacent leg, or the hypotenuse, you choose. Choose any two of those three sides.
Opposite hypotenuse.
Opposite and hypotenuse. Now, which is the opposite of this angle? Okay, and which is the hypotenuse? Got it. Okay. Now, how does this angle relate to the opposite and hypotenuse? You want to name the angle so we'll have something to call it?
Yeah, this is really throwing me off.
Okay. What you want to name it? Say again? Pick a name.
Q.
Q. Okay. Let's name it Q. Angle Q. So, how will the opposite side and the hypotenuse relate to angle Q? Which trig function? Sine. So the sine of Q is equal to, you tell me, 56.1 over, okay, 57.3. Okay, I think we can do that on our calculator. 56.1 divided by 57.3 gives you a number, doesn't it? Better be between what and what? Okay, and then what do we do with that? If the sine of Q is equal to that,
I didn't take the sign of it.
not the sine,
Oh.
what do we do? That number you just gave, 0.97, whatever it was, what do we do with it to get the angle Q? What? You do if the sine of Q gives you that, how do you get what the angle Q is? How do you undo a sine? That's twice. No, okay. How do you undo a sine? If you know this sine, say again? No. Okay. Multiple choice for me. Inverse sine, of course.
Every time I use inverse, you're like, no, let's not call it inverse.
No, that if you're talking about dividing, that you don't. Okay. Inverse sign. The inverse of 0.97 or whatever you got on your screen there, that should give you Q. If you're in degree mode.
75.9.
Ah, that sounds pretty reasonable. 75.9 degrees. There we have it. Let's see what they got. I don't even see where they write the answer down here. Yeah, there it is. They do 78.1, the 0.2. And we got 75.9. You may have rounded off a little early. Okay. I don't know. I don't have a calculator. You're in the right ballpark. Okay. We got 75.9, but they got 78.1, 0.2 approximately. Can't, huh?
I guess I did round off a little too early.
Okay.
I got 78.3.
78.3. And they got 78.2. Okay. We're close enough. 78.3 degrees. All right. That was enough like being a dentist that I think you probably need to go home or after class do the checkpoint. Make sure that you can reproduce those. Okay? Any questions on that? All right. So, here's how they do it. They started the same way y'all did. For the angle at B, going back to here, this angle B here, it's not the obtuse angle B, but the acute angle B was 90 minus 54 was 36. That's exactly how y'all started. And then from there, the two sides of that triangle there, BCD, which is BCD, that triangle we started with, B was equal to 20 times the sine of 36, and D was 20 times the cosine of 36, or you could use Pythagorean theorem, either one. And now they choose to do really strange things here. It's exactly what you did. We actually got numbers for those, and then they left them as letters, but they did the same thing, B and D plus 40. Remember, that was our 56.1, and the B was whatever that was. But then they used a tangent. They didn't use sine. Doesn't matter. We went on and figured out what the side C was, but it looks like to me they really made it difficult looking, but it's the same thing we did. And they come up with that for the tangent. So using the inverse tangent or arctangent, they got the angle to be radians. Why did they go to radians? I don't know. But then they said that's about 11.82 degrees. Nowhere in the world they could get that kind of precision. I would say approximately 12. We got 11.8. Fine. Okay. About 12 degrees. Okay. Now, so subtract that from 90, and you get, that's where they got the 78.18. We got 78.3. Okay. So the bearing of the ship is north 78.18. I would say 78 degrees west. Okay. Finally, the triangle ABC, you have sine of A is equal to B over C. Now, you don't have to do it this way. This is how they did it. What y'all did with Pythagorean theorem should give you very close to the same answer. It's just theirs looks a lot harder, but it's not. It's still pretty straightforward. Then C is equal to B over sine A. And if you plug those in, and they still are using B as 20 times, why don't they write a number down? They got about 57.4 nautical miles. I think we got 57.3. Okay. I would have rounded either of those to 57. All right. Good deal. All right, harmonic motion. What do we mean by harmonic motion? What do we mean by harmonic motion? Any ideas? If you see the word harmonic, what comes to mind? Yes, you think of a harmonica, which is a musical instrument. It's not surprising you think of that, because musical notes, frequencies, everything else follows sinusoidal curves, harmonic motion. Anything that repeats itself over time. And to get our harmonica with one note, you're repeating the same sound wave over and over again. So it's a different note, different sound wave, okay? But they're all sine or cosine waves. That's what harmonic motion is all about. The periodic nature of trigonometric functions is very useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by wave motion. Think of what all we've covered there. Vibrations, that could be what is making the sound when you blow in the harmonica? Okay? Yeah, the air is, but ultimately when you're blowing it, if you ever took one apart, you would see there was a little metal thing there, and what you're doing is making that vibrate. And that's sending out a vibration. The vibration comes through your ear, and that's harmonic motion. Vibration. Oscillations. You might say that thing is oscillating between 2 points. Okay, rotating. How about the Earth around the sun? Okay, the moon around the Earth. All those are rotations. The Earth spinning, that's a rotation. Guess what? That's what sets up our day, night, our seasons, all these things that repeat themselves over and over and over, harmonic motion. Or is moved by wave motion. What you described in the air is wave motion. A sound is a compressional wave. Okay? There's compressions and rarefactions. Compressions and rarefactions. When your ear receives that, your eardrum vibrates, a little cilia in your ear. They react to that, and it sends a message, and you translate that to a sound. Aren't you glad you have that so you can hear me? Yes, you're so happy to be listening. Okay. Anything that corresponds to wave motion. For example, consider a ball that is bobbing up and down at the end of a spring. Or maybe if your shock absorbers are shot and you hit a bump and you do like this for a while, okay? That's harmonic motion, okay? So, if you have the ball here, and this is where it normally sits. If you just hang it there, the ball has a mass there, it stretches the spring a certain amount, it hangs there. Perfectly happy right there. We call that its equilibrium position. That's what we call it, 0 centimeters. Now, if you were to take that ball and stretch it down here to minus 10 centimeters, which to me would be like positive 10 centimeters, whatever, stretch it down till it's here, now the spring is trying to pull back on you, isn't it? Okay? So if you release it from here, what's it going to do? It's going to start moving that way. Now when you release it, it says 0 velocity, right? Because you had it at 0. The moment you release it, 0, but it starts moving up, right? So it starts picking up speed because the spring's pulling it upward. And the more the spring pulls, the more speed it picks up. So when it gets to its equilibrium position, does it stop? No, it can't, because it's got all that speed going. So it starts compressing the spring until it goes up here to plus 10 centimeters. And then it's compressed the spring just as much as it stretched it here. So then it stops. And finally, when it stops, what does the spring do? Push it down again, and it goes right past, and that's simple harmonic motion. So you get to this thing, push it down, and it just repeats that over and over. Almost ad infinitum, but not quite, because the spring's not perfect. Air resistance is there. Over time, it will stop, but for a while, it does that simple harmonic motion. If you were in a vacuum in a perfect spring, it would keep going forever. Okay, nothing's perfect. Except my trig students. Right? Never mind. Okay. So, suppose that 10 centimeters is the maximum distance the ball moves vertically upward or downward from its equilibrium position how would that relate to a trig function? Hey, that would be your amplitude, exactly. 10 would be your amplitude from that equilibrium position. Suppose further that the time it takes for the ball to move from its maximum displacement above 0 to its maximum displacement below 0 and back again is 4 seconds. What would we call that? The period, exactly. To go one complete cycle, that would be the period. So t equal 4 would be our period. Your amplitude would be 10 centimeters. Assuming the ideal conditions, like a perfect elasticity, no internal friction of the spring, no energy loss to heat, which you always have, no friction, no air resistance, the ball will continue to move up and down and up and down in a uniform and regular manner, following a sinusoidal curve. If it started down here, that would be a minus cosine curve. If it started up here, that would be a plus cosine curve. If it started right here and you pushed it, got it moving, threw it downward, that would be a negative sine curve because it's going down first. If it started here and you pushed it upward, that would be a positive sine curve. So you could describe any one of those motions, whether a sine or a cosine curve, given a plus or a minus or something like that. Okay. For the spring, from this spring, you can conclude that the period, or the time for one complete cycle of the motion, the period is 4 seconds. Its amplitude, maximum displacement from equilibrium, is your 10 centimeters. Its frequency, now we haven't talked about frequencies yet, but the period is seconds per cycle. What's frequency? Cycles per second. Cycles per second. And that would be 1 over your period. Always. Frequency is 1 over period. Period is 1 over frequency. So that would be a quarter of a cycle per second. Because if it takes 4 seconds for it to complete one cycle, that means it does a fourth of a cycle in 1 second, and that's your frequency. The motion of this nature can be described by either a sine or a cosine function. It's called simple harmonic motion. Okay? So here's the definition of simple harmonic motion. Bottom of page 333. A point that moves on a coordinate line is in simple harmonic motion when the distance d from the origin at the time t is given by either one of these. D is equal to a sine omega t, or d is equal to a cosine omega t. Now, of course, you could have other variations too. You could have a phase shift in here, and you could have a vertical displacement. But this is a simple one. Where a and omega, and by the way, that little symbol there is not a W, it is an omega. It's a lowercase omega. Uppercase omega looks like a horseshoe. Lowercase omega is a little W. Okay? Where a and omega are real numbers, and we always use omega being positive. Okay? That's your B. We don't ever let B be negative. It's always positive. The motion has an amplitude of absolute value of A, just like it did before. And the period, where this used to be the B, we now call it omega. The period is still 2 pi over omega. The frequency then is omega over 2 pi. So, we give a different name to that omega. I don't know if they're going to mention it. I think they will later. What we call this is the angular frequency, because the thing in here is an angle, and if that's time, this would be radians per second times seconds would be radians. So it's an angular velocity and or angular frequency, and the actual frequency would be radians. Okay, because it's the reciprocal of the period. Does that make sense? So here is example 6, which I think is at the top of page 322. 334. Simple harmonic motion. Write an equation for the simple harmonic motion of the ball described in this figure here, 460, which I think was the same one that we used before. Yeah. Okay. Where the period is 4 seconds, just like it was before, and then it says what is the frequency of that harmonic motion. Basically, I already gave this, but we'll do it. Okay, so here's equilibrium. If we're starting from equilibrium, which function would you think you'll use, sine or cosine? If you're starting from equilibrium. Starting from 0. Sine, yes, I would go with sine. I have a feeling they'll use cosine. I don't know why, but okay. And since the first motion is downward, then that's going to be a minus sign, because usually sine goes up. So minus sine, okay, is going to be a minus there. And what do we say this was? That's your A. A will be 10. Except since we're starting going down, it'll be a minus 10. So write an equation for simple harmonic motion. I would say, when I call it y, is equal to minus 10 times the sine of, now we got to figure out what to put there. What usually goes there is our omega. Now we have to sort of work backward with this. What they've given us is a period of 4 seconds, right? So period of 4. Okay. Now, we need to kind of move backwards from there. What would be, what we are calling omega, we used to call B. What was the relationship between period and B? 2 pi over B, but now we're not using B anymore, we're using omega. So just change that B to an omega. It's just that in harmonic motion you usually call it omega. So if we want to know what omega is, we divide by 4 and multiply by omega. That would be omega is equal to what? Pi over 2. So that would be pi over 2 times t. Assuming that, yeah, since we're using time seconds, yeah, pi over 2 times t. All right, I think that has it for us. But the next question is, what is the frequency of that harmonic motion? What would that answer be? What is frequency? Okay, frequency, the easiest thing is 1 over your period, right? And what was our period? 4 seconds, so that would be 1 over 4. And that would be cycles per second. So the second answer, frequency, is equal to 1 over 4. Now, if you want to say cycles per second, you can write it out. Cycles per second. Sometimes they say CPS. That means cycles per second. Other times they just say per second, because a cycle really isn't a unit. So they'll sometimes say 1/4 per second, meaning 1 over second. The actual unit for that is Hertz, named after Heinrich Hertz, a German, I believe he was a German physicist who did some of the early work with frequencies. So per second, CPS, cycles per second, written out cycle per second, however you want to say it, that's what frequency is usually given in. And EJ is here. Good news from the doc? Yeah. All right, EJ's here. Yes. Okay, yeah. That means 1 over S. Yeah. this is a unit, okay? Per second would be 1/2 second. There's nothing to put in the numerator, so they usually do that s to the minus 1, meaning the s is in the denominator. That's the same as 1/4 per second. That's just weird not to have anything on top. That's why they like to say cycles per second, so you have something on top. But really, a cycle is not a unit, so it's just a per second, which is a second to the minus 1. But then, to have to keep from getting into these discussions, just call it a hertz. Okay. All right. I think we beat that to death. Let's see what they do with it. Because the spring is at equilibrium, D is equal to 0 when T is equal to 0, they did use the sign. Good for them. They usually use something different. Okay? So D is equal to A sine omega T. Now, I called it Y, they called it D. Doesn't matter what you call it. Moreover, because the maximum displacement from 0 is 10, the period is 4, we have the following: the amplitude is absolute value of A, so that's going to be 10, okay? So that would be your A, except, I don't know if they do this. No, they don't, okay? The period is 2 pi over omega. The period was 4, so the omega is pi over 2, exactly like y'all did. And then, so the equation of motion is 10 sine pi over 2t. Now, that would be absolutely correct if the first motion was upward. I thought by their picture it looked like it was downward, so that's why I put a minus 10 there. It doesn't really matter. It's going to go up and down, so you can start it wherever you want to. Start it going up, it's positive 10. Start it going down, it's negative 10. So it doesn't really matter. Okay? And note that the choice of A equal 10 or negative 10 depends on whether the ball initially moves up or down. By the graph, it looked like it was going down first, so that's why I did a minus 10. They chose to go up first. The frequency then is, and why do they go back to that? It's certainly true, but it was even better 1 over period. The frequency is the inverse of the period. So since the period is omega over 2 pi, which we just calculated omega given the period, why didn't you just go back and use the period? But they did. Omega over 2 pi, so that would be pi halves over 2 pi, and that would be, the pi's cancel out, and it would be pi over 4. 1 over 4th. Cycle per second. They actually write it out, cycle per second. Okay. Much easier if you'd have used 1 over period. That would have got you there in one step. All right. There is a checkpoint on that one too. Not a bad idea to do that checkpoint. One illustration of the relationship between sine waves and harmonic motion is the wave motion that results when a stone is dropped in a calm pool of water. The waves move outward in roughly the shape of a sine curve. If you picture this, I'd say this is a cosine curve. If you start here, max, you go past equilibrium to min, to max, to min, to max, to min, to max. If you drew that out, you'd have, if it started here, you'd have a cosine curve. And they said sine or cosine curve. It's shown here. If it started out right at equilibrium, then that would have been a sine curve. If it's down at the bottom, it would have been a minus cosine curve. But whatever. It gives you a sine or cosine wave. Okay. Now, but water, just like everything else, has internal friction. So in time, those waves die out. They don't keep going up to the full amplitude. Okay. Internal friction of the water. Believe it or not, water has friction. As an example, suppose you're fishing and your fishing bobber is attached so it does not move horizontally ever. It just moves up and down. As the waves move outward from the dropped stone, your fishing bobber moves up and down in simple harmonic motion. Okay? If it started even and then the rock hit and it splashed up, it would be going up and then back to equilibrium, down, back to equilibrium, up, down, and so on. Now what these other curves are showing that later in time, because this is just XY here, there's no time here, later in time it here, and then here, and then here, and here. So that sine wave is just moving down, and your bobber is going up and down. To me, it's not a particularly enlightening illustration, but I know what they're talking about. Okay? Now, they skip example 7. So let's go back and do example 7. We'll do it here. All right. Given the equation for simple harmonic motion, and they give you the equation, this time it's going to be 6 times the cosine of 3/4 pi times t. That's the one we're going to use. So let's just start over. D is equal to that. 6 cosine 3 pi over 4 t, 3/4 pi t. Find A, the maximum displacement. Anyone want to hazard a guess? 6. That's your amplitude. Now they don't give us units, so all it is A is equal to 6. Got it? The B part is the frequency. Now this time we aren't given period or anything else. We're just given, what is this symbol here? What does that represent? 3/4 pi. What's that be? That's your omega. Okay, so your omega is equal to 3/4 pi. Now, if you're not happy or used to or comfortable with omega, change it to B, because that was exactly what we used to call B, right? Okay, and what is omega then, or B? Okay, say that again. We know that the, and by the way, well, okay, let's start over. Okay. The B was, hopefully you remember this, right, is the period is 2 pi over the period. I'm sorry, I'll write it backwards. Okay. Now, most of the time we did it the other way. We said period is 2 pi over B, right? But you can just multiply both sides by B and divide by period. You got it. So B is equal to 2 pi over period. Okay? So therefore, what is period? I just said it. 2 pi over B, but we've been using omega, so let's go back and use omega. Okay? So really the period is just 2 pi divided by this omega. So that would be 2 pi divided by 3 pi over 4. Okay? So the 3 pi is in the bottom, the 4 is on top now. The pi's go out, and what do we left with? Say again? Yeah, 8 over 3. That's your period. But your frequency is 1 over the period. So the frequency is 1 over the period, and that would be 3 over 8. Yeah. First we started with omega, which is the same as B. And that B was 2 pi over period. So get the period is 2 pi over omega. So this is your omega. So put the 3 pi over 4 here, 3 pi down here, 4 up there. Pi's cancel out. So this would be 8 over 3. And your frequency is 1 over the period, which would be 3/8. This would be in hertz, or cycles per second. This would have been in the 8/3, would have been in seconds. Okay. Well, they didn't say what unit. They just left it blank. Okay. So, all right. So there's your frequency. Now, the C asks for the value of D when T is equal to 4. Okay, we're looking, and we're given the formula. D is equal to cosine, my pen is really slow, I don't know why, cosine of 3 pi over 4 T. Okay, and the C part is asking what is D when T is 4. So plug in a 4 here. D of 4 would be cosine of 3 pi over 4 times 4. Obviously the 4's go out. And what is the cosine of 3 pi? It's the cosine of 3 pi. -1, perfect. It's 1 period. Subtract 2 pi from 3 pi and you get 1 pi. What's cosine of pi? -1. So the D part would be D of 4. C part would be negative. Okay, sorry. I messed it up. 6 times that. Okay. So 6 times -1 would be -6. Sorry about that. I left off my 6 there. Okay. The D part, as opposed to D. The least positive value for T, of T, for which D is equal to 0. The least positive value for T for which D is equal to 0. Okay? So you want, let's go back to our formula. D is equal to 6 cosine 3/4 pi. No, 3/4 pi. It's not writing. I don't know why. Okay, there it goes. T. There's your formula. Okay? We want the least positive value for T for which D is equal to 0. Okay? When T is equal to 0, cosine is what? T is equal to 0, cosine is what? Where does cosine start? Sine starts at 0. Yeah, +1. So we know it's not T equals 0. So we got to move forward. Now, cosine starts up here. Where is it that it crosses it becomes 0? Where is that? Okay, it starts at 1. And T is equal to 0, goes down to 0. What is T then? T's going down, goes to -1 at some other value, comes back up to 0 again, and it goes back to 1. What's that? What is the cosine going through then? Starting at 1, going back to 1. 2 pi. The whole thing has been 2 pi. The 3/4 pi T has been 2 pi. Okay? We don't want that. We want that here. Well, halfway between that, it was at -1. So that, what would that have been? If it was 2 pi to get there, okay, that would have been pi. Well, this is exactly halfway between there. It was at 0. So that would have been ½ pi. So this thing right here would have been pi halves. So 3 pi over 4t would have been pi halves. That would have been your first 0, the first positive value of t for which that would have been 0. Solve that. How would you solve that? Just pretty simple algebra. Second? Okay, multiply by 4 over 3 pi, right? Multiply by the reciprocal. Multiply it on this side, multiply it on this side. 4 over 3 pi. See here, the 4's go out, the 3 pi's go out, you're left with t. Here, the pi's go out, 2 will go in the 4 twice, and what would that be? 2/3. T would be 2/3. We assume that's in seconds, but they don't say. All right, let's look at what their answers were. The maximum displacement would be 6, and that's what we said, 6. Number B, the frequency, it was 3/8 of a cycle per second, whatever that is. Well, we don't know if it's seconds. 3/8 of a cycle per unit of time. So 3/8. That's all they left to ask. The C part, that was at -6. And D is equal to 4. T is equal to 4. The displacement would have been -6. And then the D part was the first time that it's 0 would be T equal 2/3. Whatever that unit was, 2/3. Does that make sense? Okay, folks, that does complete section 4.8. Do we have time quickly to do vocabulary, or want to start with that next time? Let's do it now. A blank measures the acute angle that a path or a line of sight makes with a fixed north-south line. Bearing, exactly. Number 2, a point that moves on a coordinate line is said to be in simple blank blank when the distance d from the origin at the time t is given by either d is equal to a sine omega t or d is equal to a cosine omega t. Simple blank blank. What were we just talking about? Harmonic motion. Perfect. Number 3, the time for one complete cycle of a point in simple harmonic motion is its time to go from one to another. That's 1 period. Exactly, 1 period. And number 4, don't leave yet. The number of cycles per second of a point in simple harmonic motion is its frequency. Exactly. The reason I said don't leave yet, remember, today's a special day. We get your second test. And some of you haven't turned in your first test. Shame, shame. Okay. I wish I'd have got this before Amber left. She left early. Need graph paper? Need graph paper? Need graph paper? Okay. Now, I'm guessing you might need 2 sheets. Whoa, I asked her to do it duplex and she did it simplex. So I'm going to give you 4 sheets. Are you really old there? No, actually, I think I was. Okay. You need graph paper?
Oh, yeah.
Okay. So I'll give you 4 sheets because there's 9 to graph. Okay, you need graph paper? Yes. Oh, you do? Oh, you need another test. Yeah. 7:45 until 1. So working on that. Okay, you could. Are you going to be up this campus? Oh, I mean, you will be. You can slide that in my door. No, I won't be here.
Oh, okay, fine.
You can slide that in my door and I'll pick it up. You haven't started it, have you? Okay.
Taking it here.
What's that?
Taking it here.
You can if you want to. There will be a class coming here at 1:15. You should. Okay. You did turn in the first quiz, right? Yeah. Okay. Do you need graph paper? Okay. I know you don't want the keys, so here is. Glad you agreed with me so readily.
If you want to give it to me.
Huh?
If you want to give it to me, I'll take it.
All right. So if you want to work here, you certainly can. Did you have any visitors this morning? Were you in Space Lab? No students came by?
Or no, I'm doing the space lab this afternoon.
Oh, is it? Okay.
I was in the computer
you're-
lab, the freshman academy, whatever you want to call it. That's where I was this morning.
Oh, I see. Okay.
But
Is the day your class day? Music?
that's Monday, Wednesday.
Monday, Wednesday.
You're all mixed up.
Yeah, well, I thought you did tutoring on the mornings you weren't in class. Oh, you know.
Tuesday, Thursday, 1:30 to 2:30.
Oh, okay.
And I could actually probably change that now that my mini term 2 is over. But anyway, I went by the library because I was kind of bored and had some free books laying around.
Oh, really?
Yeah, I had rented my physics textbook, so
Uh-huh.
I figured I could probably put this to use at some point.
Right.
And also I saw this one. So,
Ah.
decision analysis.
Right.
Interesting.
All right. I'll be down in
They
a
were
few minutes.
begging people to take this.
Really?
I'll help you load them up. Just
Right.
bring a truck.
Okay.
Like, okay.
They don't want to haul them away.
All right.
Okay. I'll be down shortly.